Hello everyone, I'm Alkush. In this video, we will solve one problem in Chapter 11. A bar of mass M and length D shown in the figure can rotate freely about point O. A lump of duff with mass m, which is M over 3, and speed v strikes the bar at distance d, which is 2 D over 3, measured from point O and stays there. The rotational inertia of the bar about the pivot is 1/3 M times d squared. Determine the ratio of the final kinetic energy just after the collision to the initial kinetic energy just before the collision of the bar-duff system. Before solving the problem, let's have a look at the analogy between linear or translational and rotational motions. Linear motion is described by the parameters mass, linear distance, linear velocity, linear acceleration, force, and linear momentum. On the other hand, rotational motion is described by the parameters moment of inertia, angular distance, angular velocity, angular acceleration, torque, and angular momentum. Linear momentum is defined by the formula m times v, where m is the mass and v is the linear speed of the object. On the other hand, angular momentum is defined by the formula moment of inertia times the angular speed. Kinetic energy of an object under linear motion is defined by the formula 1/2 mass times the linear speed squared. If we multiply and divide this formula by m, we obtain 1/2 mv squared over m. Since mv is linear momentum, then we obtain p squared over 2m. Similarly, kinetic energy of the rotational motion is 1/2 I omega squared. If we multiply and divide this formula by I, we obtain 1/2 I omega squared over I. Since I omega is the angular momentum, we obtain kinetic energy of the rotational motion as L squared over 2I. Angular momentum of an object about point O is defined by the formula L equals R cross P. By the right-hand rule, the direction of the angular momentum is towards U. Because of the cross product, angular momentum has the magnitude R times P times sine theta, where theta is the angle between P and R. According to this example, component of the linear momentum perpendicular to the line of extension of position vector is calculated by the formula P times sine 180 degrees minus theta. If we use the trigonometric identity here, since sine 180 degrees is 0 and cosine 180 degrees is -1, then we obtain P perpendicular as P times sine theta. Then the magnitude of the angular momentum is found by the formula R times P perpendicular. Linear momentum is defined by the formula m times v. Because mass is a scalar quantity, then P and v have the same direction. Therefore, P perpendicular becomes m times v perpendicular. As a result, magnitude of the angular momentum L becomes R times m times v perpendicular. Total angular momentum just before the collision, L initial, is equal to the sum of the initial angular momenta of the bar and duff. Since the bar is initially at rest, its angular momentum is 0. And the initial angular momentum of the DAF is found by the formula r times m times v perpendicular. V perpendicular here is v times sine 60 degrees, which is square root of 3 over 2. Position vector is measured from point O, so r is d. Therefore, we end up with the initial total angular momentum of the bar DAF system as square root of 3 over 2 times dmv. Torque has the formula R cross F. Since force F has the formula dP over dt, we can write d over dt R cross P, since dr over dt is 0. Here R cross P is the angular momentum, therefore net torque becomes dl over dt. Remember that derivative of a number or a constant quantity is 0. Therefore, if there is no external torque on the system, then angular momentum L is conserved. This means that initial angular momentum is equal to the final angular momentum. In the example of the bar DAF system, there is no external torque. Therefore, initial angular momentum is equal to the final angular momentum of the system. This is to say that LF equals square root of 3 over 2 dmv. Just after the collision, the final total rotational inertia about point O is the sum of the rotational inertia of the bar and DAF. I bar is given as 1/3 capital M times capital D squared. And I DAF is M times D squared, because rotational inertia is calculated by the formula M times R squared. Capital M is given by 3M. And capital D is given by. Therefore, the final total rotational inertia of the bar DAF system becomes 13 over 4 md squared. The initial kinetic energy of the system is due to only the lump of DAF, which is calculated by the formula 1/2 mv squared. The final kinetic energy of the bar DAF system is found by the formula Lf squared over 2If. We know Lf and If. After some cancellations, the final total kinetic energy of the bar DAF system is found by 3 over 26 mv squared. We obtain the ratio of the final kinetic energy to the initial kinetic energy of the bar DAF system as 3 over 13, or approximately 0.231. Okay, this result brings us to the end of the discussion of this problem. Thank you for your attention. See you in the next video.